Welcome one more time to our next presentation. This time we're going to be talking about cybersecurity investigation with Jupyter notebooks. Jupyter notebooks are growing in popularity about CyberSec analytics for threat hunting and incident investigation. Notebooks give you the flexibility not found in security operations centers toolsets. However, threat hunters require specialized tools, analytics, and visualizations that aren't part of the typical data science libraries. The focus of this presentation will be on Python techniques that can be used to build extensive and discoverable tools for large-scale cybersec operation. This time, our speaker, Ian, who works as a principal developer in Microsoft Threat Intelligence Center, where he spent most of his time building and maintaining Microsoft CyberSec hunting Python tools libraries and creating notebooks for threat hunting and investigation. Prior to this, Ian used to work on Azure Security Center. Some notes: he loves skiing, snorkeling, and scuba diving, music, and occasional messing around with Raspberry Pi and MicroPython devices. Thank you very much, Ian, and let's get to your talk.
Hey, thank you very much. Kind of real privilege to be here. I was a bit torn in the talk whether to talk about cybersecurity aspects or Pythonic aspects of like how we built the thing. So I've ended up with a bit of a hybrid. That'll either satisfy a lot of people or maybe satisfy nobody. But I hope hope there's something in there that's interesting.
Yeah. Thank you again for being here with us, and let's start your presentation.
My pleasure. Hello, and welcome to Cybersecurity Investigations with Jupyter Notebooks. My name's Ian Hellen. I'm a principal developer at the Microsoft Threat Intelligence Center. So we're starting off with some background. Then we're looking at queries and getting data, looking at enriching data, visualizing threats, and finally putting it all together. And there are a number of workshops and videos you can find out there that describe some of the features of MSTICPy, but today we're going to be looking more at the architectural decisions, some of the coding techniques we use to get around specific problems. So there's a companion notebook that tracks the demos you can see here. You can download this from this URL. What makes Jupyter such a good fit for the InfoSec world? Firstly, there's the Python Jupyter ecosystem. So accessible technology, open source, means there's a very low barrier to entry. A huge variety of packages such as pandas, requests, Boker, giving you easy access to rich functionality. And Python itself gives a very low bar to entering coding. Jupyter specifically, you can break out of the proprietary constraints of many SOC tools. You can control your own workflow, you can create custom visualizations, and bring in custom analysis. The notebook format itself allows you to blend code, text, visualizations. It auto-saves your progress, and you have a shareable document format. Moreover, you can reuse a notebook in future investigations and hunting. And there's a lot of enthusiasm out there for Jupyter and InfoSec. Roberto Rodriguez, known as Cyber War Dog, in social media and on GitHub, has organized the last 2 years the InfoSec Jupyter-thon. And we had several hundred people attending the beginning of December to share ideas, participate in workshops about using Jupyter notebooks in InfoSec. Check it out at this URL. Many Jupyter and Python features are shaped by their origins in the scientific and data science worlds, and this is not always a great match for InfoSec needs. So an InfoSec analyst needs typically many log sources. They need access to a set of templated queries and a consistent access pattern. So regardless of where the log comes from, it should work. The query should work in the same kind of way. They also needs to access specialized data such as threat intelligence, geolocation information for IP addresses, analytics. So data in the InfoSec world is predominantly text rather than numbers. So this does mean that many of the things like machine learning models, examples, rely primarily on numeric information, not always very applicable to InfoSec. Visualization, the third area. So even though there are a lot of great sophisticated packages out there, InfoSec analysts needs a number of domain-specific visualizations that are just not available. And there's a lot of enthusiasm for using Jupyter kind of to break out of the standard security operations toolsets, known as the SEAMs. But there are hurdles to that. So even though people want to do it, there's a bit of a learning curve attached to just setting up a Jupyter infrastructure. So we wrote MSTICPy. It was originally a very modest project a few years ago as a means to try and close some of these gaps. It's an open source toolset, primarily aimed at Jupyter notebooks, but also usable in Python apps and scripts. It has a few different main component areas. So there's a lot of emphasis on data access and queries, a whole set of enrichment functions, some visualizations, and some analysis components. And we'll look at some of these later in the talk. So let's look at the first of those, data and data providers. Analysts need lots of data, and often from lots of different places. So if we're building a data provider for those analysts, we need to be able to mask the different access methods they use, potentially the different query language, different authentication requirements. We need to give them access to parameterized queries so they can rerun the same kind of pattern over and over again. And at least in our case, we always return pandas data frames. We have a whole bunch of drivers. What is Microsoft Sentinel, Microsoft Defender, Splunk, Sumo Logic, local data, a few others that are more arriving all the time. And our solution is a relatively straightforward one. We have a query provider, and when you instantiate one, you give it the driver name. This tells it which backend to use. There's a relatively simple set of interface methods. Connect to authenticate, list queries to see what queries are available, and to run a query, that's also a method of the query provider. So you supply parameters that are injected into the query, runs and returns results. And we didn't invent all of this. A lot of this is borrowed from Intake, which is a Conda project for data access, primarily for data science. So some of our requirements, we wanted the queries to be in a declarative format. So we store them in YAML, and if there's an Intake people out here, they'll recognize the schemas is very, very similar. But we want the queries to be runnable as methods on our query provider to pass the parameters that are required by the query. We'd also like those functions to pull informative help from the query metadata to tell us what parameters and the parameter types. And we'd like our query provider to manage time ranges for our queries, and that can inject the start and end time into any queries we run. So let's have a look at a demo of how we constructed our data provider to meet some of these requirements. In this demo, I'm going to be showing you how we built our data query functions from declarative data. Here we can see a function definition defined as a Python dictionary. It has a number of properties, the name, the query we want to run with substitutable parameters, and the parameter definitions with type and description. We've created a class to hold this definition. The init function simply assigns the dictionary values to internal attributes, and the create query uses the Python string format to substitute any passed parameters into the query string. If we run that, we can see how it works. So let's add a couple more queries. Really, you would normally store these in a YAML or JSON file and instantiate them into Python dictionaries. So we need a fake driver. This would be Splunk or something, and it has a couple of methods, a connect and exec query. The exec query just returns some faked results. And then we need a class to hold it all together. So this has an initializer, which creates a driver, and this normally would be selected based on the name of the driver. But here we're just statically adding a single driver. We have our connect function, which is just a pass through to the connect that we defined in the driver, and our all-important exec query function. This is the thing that's going to run the queries, and it calls the definition as create query, and then sends that query with the substituted parameters to the exec query function. And we just create an instance like this. So let's load our query definitions that we defined in that dictionary. We first of all create a query instance from each dictionary item. The next step is where the magic happens. We import partial from Python functools library. Now partial creates a version of the function with some of the parameters already substituted. In this case, the function we want to do that to is the exec query function, and we're going to substitute the query def parameter. And if we look back at our query provider class, we can see exec query takes two groups of parameters: the query definition itself, the function definition, and a bunch of variable keyword arguments that it will pass to create query. Next, because we want to be friendly, we can create a docstring where we insert the description from the function definition. And finally, we set it as an attribute. So we add this function as an attribute with the definition name to the query provider. And if we look at the members, we can see here we've got a new basic and get user methods, which are these functools partial methods. We can check, does our help work? Not very pretty, but we have the description that we defined in the function definition. Do they work? Yep, we can see the parameters, host and host table substituted, and the fake results. And for the other query, same thing, where username equals Ian. This is what our query examples look like. Some other examples of Splunk and OData providers. And how does it work in the real MSTICPy? So here we have 3 lines where we instantiate the query provider, connect, show a list of some of the queries that are available for that provider. We can see the help. This is a bit more elaborate than our toy demo, but you get the idea. And running a query. Now we have a function that we've dynamically added to this query provider. We provide it the parameter, and it runs and returns the results. We can look at our built-in time range, and perhaps we want to alter the time range. And we can have multiple of these providers. So here's another one for Azure Sentinel, where we have a different set of queries available. So in our second section, we're going to be looking at enrichment. So what do we mean by context and enrichment? So let's take an entity such as an IP address. When an analyst sees this, there are questions like who owns this IP address? What is the geographical location? Are there any threat intelligence reports that may indicate that it's malicious or has a malicious origin? Similarly for things like an account, when did it last log on? What access does it have? Is there any suspicious activity associated with it? And the same for other kinds of entities like hosts, URLs, files. The more context we have, the more understanding we have of, is this part of some malicious act, or is it just a bit of noise? So an ideal enrichment or context function should have a few different characteristics. So contextual data, contextual functions need to be specific to the entity that the context is about. They need to be easily discoverable, and they should work in roughly the same way. So they should have common parameter set, return data types that are the same kind of type. So our initial approach in MSTICPy, we built a bunch of enrichment functions in a little bit of an ad hoc way. So geolocation, domain and IP ownership, threat intelligence, a few others. So some of these are extensible, so there's some consistency within them, but not so much between them. If we look at our checklist, on the whole, we kind of fail in every one of these. So we don't have any special association between a context function and the entity that it relates to. You have to know, it's not particularly discoverable, you have to know where to import it from. And every function works a little bit differently. The input parameters, The names and the types may be slightly different. The output format, maybe whatever we were thinking of, which was a good idea at the time. So how did we approach making this better? So we built entity classes, and these are simple holders of a few properties. So there's an example of an IP address. So we have the first part. We have like, this is what we can hang the functionality around. But we'd already written the code. So maybe we could wrap the functions we'd already written to give more consistency to the interface, and then dynamically attach these functions to the entities so they're all grouped logically. So let's have a look at what life was like before pivot functions. Now, pivot functions here are the wrappers that we created to wrap up different kinds of context functions to make them work in a very similar way. We can see we had to know where to import TI lookup from. We instantiated an instance of the class. We provide specific parameters with the names. We then do some other operation to get the results in a data frame. And finally, we browse the results. It all works and we can see the results, but it's a bit obtuse and a little bit tedious. Similarly with GeoIP lookup, we can get the results, but it's returned in this nested dictionary form, which seemed like a good idea at the time, maybe not in retrospect. So let's have a look at what we could do to wrap these things. We define a simple function here, printMe, just takes a string and capitalizes it. But if we try to use it with a list, of course it doesn't work. So let's build a wrapper. And here we've got a function inside a function. And this is known as a Python closure. And here the func parameter to the outer function is passed to the inner function. And if you notice, the inner function is testing the type of argument that's passed. If it's a list, it will iterate over each item and call the function on each item. If it's a string, it will just execute it as normal. So we can use our wrapper, and we can pass it our original printMe function to create a wrapped function. And this returns the version of the inner function that calls, rather than func, calls printMe. Does it work? It seems to support both strings and lists, as we might have expected. But we can also use the wrapper for other things. So we define a different function, shoutMe, which does something a bit different. Do the same thing, pass it to the wrapper, and we get our input parameter independent functionality. So we can apply a similar kind of logic to output functions. Here, instead of changing the input argument, we're running the function and then checking the type of output. If it's a data frame, it returns the result. If it's something else, it converts it to a data frame. Here is a function we're going to wrap, converts string to upper. We do the same thing. If we run that function, then we see we get this output as a micro data frame, even though what we sent it was a string. So that's how we handle always returning data frames, irrespective of what the function returns. So let's put both of these together. We've rewritten our don't care function to be a little bit more sophisticated and also use the functools wraps, which does nice things like preserve stack trace and docstrings for the wrapped function. And then we have a wrapper around a wrapper. So first we call our handle input function, and then we wrap that function in our handle output function. So now we're combining both things, wrapping it twice. So let's take our toUpper function, pass it to our combined wrapper, and see if it works. And here we get 3 output data frames with different input types. So some of you might be thinking this looks a lot like a decorator. And in fact, this is a decorator, but it's used in a dynamic way rather than a static way. Let's have a look at how this works in MSTICPy. So we load our pivots, and we can see for each entity type, we have a whole bunch of context or enrichment functions. We've preserved the original function docstring. So the original wrapped function, that's the docstring that's exposed in our wrapped function. And if we look at how a couple work, here's a geolocation lookup and a threat intel lookup that so we're importing IP address entity. They're both methods now of the IP address function rather than standalone functions. We can run those and easily get geolocation and threat intelligence for the IP address. Do they work with lists and data frames as inputs? Of course they do. Here we can see we're passing a list to get the geolocation function. And the same location function taking a data frame as input. So let's take a look at visualization. So as I said earlier, InfoSec analysts need domain-specific visualizations. And some of the key criteria, time-based charts are critical, so event timelines. And there are also some specific visualization, more specialized visualization types, such as process trees and graphs, that are very useful. Interactivity is very helpful, being able to zoom in and out of like very large data sets, or hover over individual items and see more information related to that item. And finally, discoverability. It's like, how do you find out which visualizations are available? So how do we approach visualizations in MSTICPy? Most of our functions support a fairly generic input. Many of them only need a timestamp column. And we expose them all through pandas accessors. We have a bunch of visualizations that we'll look at in the next section. Some inspirations here, particularly the Bokeh periodic table in the gallery was an inspiration for how to create process tree, which we'll see in a moment. Also, I'm indebted to myRthings, who produced cat scatter, and we've kind of reproduced that in Bokeh for our matrix plot. Let's have a look at the built-in functions for visualization in MSTICPy. First here we're importing a data frame, and you'll notice that these visualization methods are what's called accessor methods for pandas, a little bit like the built-in plot function. First thing we're looking at is the timeline visualization. This shows you events against time, obviously, and these here are grouped by account, split them out into separate series. You can use the range selector to zoom in to focus on a particular time range. And you can also use the mouse wheel Bokeh control to do the same thing. As you hover over each event, you can see details of the event under the cursor. And then reset it back to the standard view. The second visualization is a subtle variation on this. This time, rather than just displaying groups in different colors, it shows the entire duration of the activity for that particular group. Useful to see things like the duration of logon sessions or particular types of process activity. The third plot type is a matrix plot, and this shows you an interaction between X and Y axis. In this case, it's IP address against a protocol, and shows you the number of events that have occurred for that particular intersection. The final visualization we're going to take a look at is the process tree. This plots parent-child relationships between processes for up to a very large number of process events. You can hover over individual items to see the command line that was used, see which account was running the process. And it can be very useful to pinpoint attacker activity on a machine. Composability. Quite a long word, and it wouldn't fit comfortably on my slide deck without hyphenation. But really just everything should work together. So ideally one function output can be the input from another function. And if you can do that, you can chain together functionality very easily for more complex and repeatable analysis. So we've done that by making everything pandas-centric. So functions in general in MSTICPy should always accept data frames as an input, and if they're going to return anything, they should return a data frame by default. And I've mentioned before that we use pandas accessors to get to a lot of the functionality in MSTICPy. In this section, we look at some of the things we talked about earlier, bringing things together in a composable pipeline. So we take here, our starting point is a list of IP addresses. We're going to pass them to the whois function from the IP address, and we have a specially defined pandas accessor that allows us to run additional pivot functions and pass them the arguments they require. And in each case, we're going to be joining the input to the output. Each one produces a data frame, and we can see the results here in a combined data frame where we have the whois information, the IP address ownership. We have the geolocation information, country, ideally the city where the IP address is homed, and threat intelligence reports, all combined into a single data frame. Here is an example of a more complex pipeline that involves threat intel lookup at VirusTotal, data query to determine whether any suspicious IP addresses have logged on, and finally it plots out to one of our visualizations to produce a timeline of any suspicious IP activity. The output would look something like this. This is our intermediate display and the final logon attempts timeline. So in conclusion, even if what you're working on seems like a quick and small project, as we found with MSTICPy, it can grow over time. And organic growth is not always organized growth. In fact, usually it isn't. So understand the special requirements of your domain and plan for discoverable functionality, consistent experience of functions and classes, and to build the right visualizations for the domain you're working in. Sometimes, because of Python's awesome capabilities, it can let you get away with retrofitting some of this, but it's always better to do it from the start. I want to thank the PyCascades organizers for inviting me to speak. It's been a lot of fun to be building this, talking to you today. I'll leave you with a slide of references. There's the notebook that covers all of the material I went through in the demos. There's our GitHub. Please leave us a star if you pass by. And some contact information, as well as MSTICPy docs and some sample notebooks. Thank you very much.
Thank you very much, Ian, for taking the time to teach us about cybersecurity investigation with Jupyter Notebooks.
Hey, thank you very much. Yeah, I wish I hadn't just watched myself. I could see all of the dodgy edits and things I wanted to correct in the video, but it was a real pleasure to be able to talk to you today.
Yeah, we really appreciate it. And the next presentation will be how not to start a Python user group with Joseph Riddle. We have a 15 minutes break now, so we hope to see you all back at 2:30 Pacific time. And also, please do not forget to check out Microsoft Virtual Booth right here in Analysts, where Ian is going to be there answering any questions that you can have.
Yeah, I'll be there at 3:30 to like a special half hour, ask me anything. Kind of within reason, ask me anything.
and again, we really appreciate and for taking the time to be here with us. Thank you very much, Ian, again.
Thank you so much.